Okay, let's keep moving. So I've just summarized what I've done so far here, where ID is now approximately equal. Okay, I have to say approximately equal because I had other terms which were higher order terms, and I have neglected all of those terms. Because I've neglected all of those terms, because delta VD is small, I'm going to be left with ID being approximately equal to the term on the right-hand side here. So let's stare at this expression, at this equation here. What do you see that is interesting about it? First of all, notice the first term, f of capital VD. So VD is a DC value. It's a fixed DC value. Okay, it's not changing with time. So right there, you notice that it is a constant with respect to delta VD. So delta VD can change all at once, but capital V, capital D is fixed. So this first term is a constant. Okay, so that's the first thing you observe. What's the second thing you observe? The second thing to observe is if you look at this term here, then that term is also constant with respect to delta VD. Okay, and in fact, that term is a slope of the function f of VD at the point VDID. Okay, so this piece here is the slope of the function f of VD at the point capital V, capital D, comma, capital I, capital D. Okay, so the first part is the slope of the function, and then that multiplies the small change. So what do I have? So I have ID being equal to a constant, okay, plus constant times delta VD. Okay, so ID is simply is equal to a constant plus a constant times delta VD. Okay, so the slope here is independent of delta VD. So what can I do next? So what I can do next is because ID is equal to a constant, I can express my ID as follows. Okay, what I can say is that my ID comprises two components. My ID has some component, capital I, capital D, a DC component, and it has some time varying component that I call delta ID. And I'm getting that because on the right-hand side, I have a constant term, and I have a constant plus delta VD, which is a term related to delta VD. And delta VD is, in this case, I'm picking it to be a time-varying term. And so therefore, on the left-hand side, I'm going to get a constant term plus a time-varying term, a small time-varying term. Okay, so I have an ID plus a delta ID on the left-hand side, and that will be equal to f of VD plus d of f of VD dVD evaluated at VD equals capital VD times delta VD. So I've just copied the right-hand side from the top. So let's stare at this for a second. I'm going to go back and refer to this equation a dozen times from now. So let me mark it with an X. Okay, let me mark it with an X. So I'm just going to refer to it as this little thing in X. So I want you to stare at this X equation carefully. What do you see here? First of all, notice these two terms here. Okay, so take a look at this ID term and take a look at this f of VD term here. Let me use a different color just to make it stand out a little bit better. Okay, so look at ID and look at this piece here. So notice right away that f of VD is simply the original equation evaluated at the point VD. What was the original equation? The original equation was ID equals f of some VD. Okay, that was the original equation for my light emitting export V. So what that is saying is that the first constant term is simply the same function evaluated at VD. Okay, and so that is equal to ID. So ID is simply the function evaluated at capital VD. Okay, no surprises, no real surprises there. Then let me take the second part. Take delta ID. So delta ID is given by the second piece here. That delta ID is simply some constant. Okay, this was a constant. Some constant times delta VD. So let me just separate out those parts and write them out as two pieces. And what I can do now is, since this is DC and this is time varying, this is DC and this is time varying by my construction, I'm going to tease them apart. Okay, so if a DC plus a time varying part of an equation relates to a DC and time varying part of another on the right hand side, then you can equate the DC and time varying components. So let me equate DC and time varying components. Okay, and the reason I can do that is when I have an equation, that equation must be true for all time. Okay, so as time changes, and if I have a DC and time varying part, and if the time varying part keeps changing, then because the equation must be true for all time, then it must follow that the DC parts must be equal and the time varying parts must be equal. Clearly, the DC part doesn't change with time, and so as that changes, it cannot influence the DC part. So therefore, the two DC parts must be equal. Okay, so therefore, the DC parts here are ID is equal to F of VD. Okay, so that is my DC part. And then I have a time varying part. And the time varying part is ID is equal to df of VD by dVD evaluated at VD equals capital VD times delta VD. And as I mentioned before, this part here is constant with respect to VD, so delta VD. Okay, so what have we here? What we have here is on the left-hand side, I have equated DC parts of the equation, and I call this my operating point. Okay, that is the operating point. And on the right-hand side, I've equated my time varying part. Aha, I caught a bug here. It should be a delta ID. Okay, so delta ID is my time varying part, and that is equal to the time varying part of the above equation. Okay, and within that time varying part, the part which is the slope of the function is a constant with respect to delta VD. Okay, so let me just make a note of that, which is that, let me pick a different color. So this piece here, the blue piece, is the slope of the function at capital VD ID. Okay, it's the slope of the function ID equals f of VD at the point capital VD capital ID. Okay, so there you have it. So I've equated the DC and time varying parts, and I've got two components to my x equation is broken up into parts.